Thanks. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this morning. We thank you, Lord, that you loved us even when we didn't love you. We thank you that you are so gracious to come to earth, die for our sins, if we'll just accept you, Lord. Thank you for your grace and mercy for us each and every day. I just pray to be with us today. Help us to glorify you and what we do this morning, Lord. In your name I pray. Amen. So guys, I told you I would give you a couple minutes to start to ask homework questions. Just go ahead. If you got them. Yes, sir.
Homework 8.4, question 28.
Yeah, we'll get to that sort of one today, hopefully. I'll put that on my list of things to try to do. Next question? Yes, sir. 8.2, number what? 58B. Ah, yes, the center of mass question. So, just a brief introduction to center of mass. So for one dimension, if you study it in physics, the finite case looks something like this. 1 over m, the total mass, the sum I equals 1 to n of x sub I, m sub I. So this would give you, if you had a bunch of masses along some line, they don't have to be, they can be all kinds of different, wherever. Maybe one way over here. So here's like, somewhere there's the origin, you know, this is x1, maybe this is x1, x2. They don't have to be in order, whatever. Anyway, you got some masses, all right, and they're at these different coordinates. Here's the nth one, I don't know, whatever. So you have mass 1 here, mass 2 here, mass 3 here, and so forth. The nth mass. So the total mass, big M, I'll give some feet to the big M, there you go, is simply equal to the sum I equals 1 to n of m sub I. All right. Now, what if instead of having, you know, a discrete collection of masses, what if you have a continuous distribution of mass? How does this change? So instead, you have something like just some sort of, maybe some sort of you know, thin rod. Maybe it has varying thickness, so you have different mass per unit length in different places. But if you pick a particular little stretch of it, let's say dx, right, then the dm in here, and you say that this has dm, then dm dx is what's known as lambda, the mass per unit length. Now this can generally be a function of x, right? And so if I want to calculate the total mass, I know you're asking me about part B, but I got to do this to set up part B, okay? So for part A, to find the total mass, what do you want to do? Well, in the continuous case, this total mass, the sum, you have infinitely many little masses, right? You take the limit as the number goes to infinity, blah, blah, blah. This basically becomes the integral over dm schematically. But pragmatically, what that is the integral, say, from a to b of lambda dx. As you can see, lambda dx is equal to dm, right? Using the infinitesimal method. And here I'm, of course, assuming that this starts at x equals to a, and it goes to x equals to b, right? So that would be how you calculate the mass of some rod of variable density, mass density. Now, part B asks you to find the center of mass, right? And so that's the continuous generalization of this idea. So this, when you take the limit as the number of masses goes to infinity, as the size of the masses get very small, what this summation becomes is a Riemann sum, and that Riemann sum basically is this, the integral over x dm, sort of schematically. All right? So this is a sort of, I could just say, this is a organizing principle. What I'm writing here, this isn't, I've never really defined such an integral, but you should have some intuition for what I'm saying. How we actually calculate that is the next thing, which is 1 over m. The the integral, in this case from a to b, of x. Well, x is x. What's dm? Well, dm is lambda dx. And there you have it. This is the center of mass formula for a one-dimensional problem. That's how you find the center of mass. You already found big M. That's part A. Right? So for this problem, it's just a very, this problem has what? Lambda equal to what? Natural log of x, is that right? And the rod goes from what to what? Problem 58. X equals 2 to x equals to 3. I'm using lambda for f of x, right? You're supposed to calculate the mass and the center of mass. So basically, to do part A, what you got to do, and I think you already did that from your question, is to integrate natural log of x dx, right? From 2 to 3. And then for part B, what you got to do is you got to calculate x bar, right? Which is going to be the integral from 2 to 3 of what? Of x, ln of x dx, right? That's what's asked of you there. So when you hit a homework problem like this, if you haven't seen that in previous work or something, if you don't want to wait for me, one thing you might do is just look in the index and try to find where he first talks about it in the book, you know. I'm saying hopeful words. Let me see if that actually fleshes itself out. I have faith in the quality of your book. You paid enough for it. There should be some discussion of it somewhere. Let's see here. We're looking at what? Center of mass? Now this is also, I guess some language might be keeping you from seeing this. This is also the centroid. If what? Centroid if we put lambda equals to 1, so I don't know if that's going to be helpful or not. No. Anybody help me out? Where did you first talk about this in the book? Anybody know? We might find it under density. Density of real numbers. No. That's not the one. Weight, 328, maybe. There's probably something in this section that I'm ignoring, right? That would be rather embarrassing, right? If it was actually in the section I'm looking at. It's probably back in chapter 6 where he discusses physics and such. I haven't found it yet. I guess it doesn't really matter if I can find it in the book or not, since I just showed you how to do it, does it? Well, I will leave it as an open question as where this is first discussed in the book. Is there another question? I think this is boring to watch me look through the book. We can do something better with our time. Next question. Is that clear? I mean, this is another kind of application that we can always ask about, right? Again, if the lambda of x is just a constant, then this gives you what's called the centroid. But no one really asks you about a centroid of a one-dimensional rod because it's just kind of like it's the middle of the rod and that's it. You don't really need calculus. It's more exciting when it's two-dimensional, so, or 3. Any other questions? Okay, go ahead. Yeah, you. You're both along the same line of sight, so it was confusing.
78A on 8.2.
Uh-huh.
When they're asking you to prove that identity, I don't know how to get the x minus b into the second integral.
Did I already collect this one, or is this a future one?
This is from Monday till Monday.
Okay, so I can show you the solution then, right? By the way, I did mean to post that yesterday, and then I just went home and fell asleep. Sorry about that. I do have a solution to post for you. I just haven't posted it. Oh, you know what? It's really hard for you to see it unless I plug it in. Strange that way, isn't it? But then again, we've grown accustomed to these wireless things. We haven't quite gotten to the point of having wireless monitors, though, right? Well, at least I haven't. Maybe there's one in Bill Gates' home. I don't know. Let's see here. We can do it. Oh, maybe I've got the wrong. Yeah, I got to switch to the HDMI source. There we go. Oh no, why did I do it that way? Hideous. We talked about a better way in class, didn't we? Let's see here. What was that again you were talking about? All right, keep going. What? Oh, it's the one we haven't turned in yet. Oh, man, why did I do this? You should have stopped me. Sorry. Let's see here. So, what we're trying to show is what? F. Yeah, so his hint is you can show this, right? F of B minus F of A is what? All right. And then, so that's not what the, he says you're familiar with that, right? And then he's like, assume F has a continuous second derivative, use integration by parts to derive this identity. Okay, so I guess I'll start with integral from A to B of the thing you don't know how to get to. So why don't we just start with the thing you're confused about, how to get that x minus b. Let's just start with it. See where it takes us. Second derivative, right? So what should we do? Here's what I would suggest we do. I think we can look at this and this as our what? Our dv. And we can look at this as u. Right? Now, we haven't done much of this, but we can do integration by parts with bounds. It's been the case that we've done mostly integration by parts without bounds. If you have bounds, they just follow along. So basically, you just feed the integration by parts formula, the fundamental theorem of calculus part 2. So here, what that looks like, what's the integral? So if dv is f prime prime, what's v? V is equal to what? Yeah, f prime of x, right? Because if I differentiate f prime, I get f prime prime. I think we can agree. So what we got then is we've got x minus b, right, times f prime of x, because that's v. I have to evaluate that from a to b. And then I have to subtract the integral of v to u, which in this case is f prime of x, right? And what's du? dx from a to b. I think if I write much more, I've solved the problem, so I should stop. But this is the start of it. Once you do that, I mean, I'll do. So, I'll tell you what. I'll do one more thing. If I plug in b, what do I get? Nah, worse. Plug in b here. B minus b, right? 0, yeah. But then this one gives me minus parentheses a minus b f prime of x, right? And then what's this? That's f of b minus f of a, right? Oh, what do you think? Think about it. What should it be? I'm not a politician. I think you should think your own thoughts, you know? I mean, I don't know what's best for you, generally speaking. I think we should be a free people. Live as individuals. I know it's an antiquated idea, but what is it? It should have been a. I mean, that was a mistake. So, because I'm supposed to put x equals to a everywhere there's an x, right? Yeah.
How do you get from that starting identity to...
Well, we just use the starting identity right here. In other words, the way to prove what's asked of you is to use integration by parts paired with that starting identity. If you're trying to go straight from the starting identity to what you're asked to prove, it's going to be a bit more difficult, yeah. Yeah, so a lot of times a problem like this, if you're kind of lost, start with the thing you're most confused about and try to go from there. In this case, it was the f prime prime times x minus b term. Past this, it's just algebra, right? I've almost solved it now. I'm sorry. Deprived you of the joy. I'll be careful not to do this in the later section. Don't tell them. Yes, sir?
How did you get that negative sign in front of a minus b?
Well, it's because it's the upper limit minus the lower limit, right? So it's the lower thing, so it gets subtracted. Yeah. Any other questions? You had a question? Was it the same question, or?
It was about 73b, talking about a reduction formula.
73b. Using the appropriate reduction formula. The appropriate reduction formula is found in problem 67. See 67? Problem 67 shows you that it tells you the integral of x to the n. Now, the one you just asked me about was what? Problem 73. That one has a equals to 1, which is nice, right? A is equal to 1 in problem 67. So we've got like x to the n, e to the x, dx. This is a formula. It's x to the n, e to the x, minus, and a is equal to 1 here, so I'm just not writing them. Integral of x to the n minus 1, e to the x dx. So that's kind of a cool formula, right? So for example, if you do integral of x squared e to the x dx, you could do x squared e to the x minus twice the integral of x e to the x dx. But then you keep doing this formula. So apply it. So that was n equals 2. Now I'll do n equals 1 to get to what's in the red. N equals 1 would give me x e to the x minus 1 times the integral of x to the 0, which is 1 e to the x dx. Of course, what's in the red is what we derived from integration by parts the other day. Was our first example of integration by parts, and there it is, x squared e to the x minus 2x e to the x minus e to the x plus a constant. This is known as a reduction formula. It kind of bootstraps your way down to the base case. There's something like this known for like most of the common functions, sine, cosine, exponential. Natural log is in problem 68, you know, so. These might be faster than some of the methods I teach. Other questions? All right. Well, we, of course, will have more time for more questions other days. But now I want to get back to the main problem at hand, which is the problem of understanding the program of implicit substitution. So implicit substitution, there's sort of two main classes of examples we'll look at: the trigonometric substitutions and also the hyperbolic substitutions. The hyperbolic substitutions aren't really exposited in your textbook much. Maybe there's a homework problem on it somewhere. But if you look at my Chapter 9 lecture notes, you'll see that I have a fair amount to say about hyperbolic substitutions. And if you look at my notes, you should be... Oh, you guys still looking at that? I see people writing, so I can only assume they're writing something I wrote. I'll stop erasing. Sorry. Okay, so let me just give you a big picture summary of what's going on here. Trig substitution and hyperbolic substitution. Tell you what, maybe I should write it over here since I want to keep it for later. Trig substitution, hyperbolic substitution. All right. So basically, these are all built around exploiting the fundamental identities for these functions. The key to trig substitution really is cosine squared theta plus sine squared theta equals to 1. Or, what's the other one? We can divide this by cosine squared. We get what? We get 1 plus tangent squared theta is equal to secant squared theta, right? The other identity we get, if we divide that by sine squared, we get cotangent squared plus 1 is equal to cosecant squared. Right? What are the corresponding hyperbolic identities? You've got cos squared. Cos squared, I'll say phi, minus sinh squared phi. Goodness gracious. Sinh squared phi is what? 1. If we divide that identity by cos squared, we get 1 minus tanh squared is equal to hyperbolic secant squared. And likewise, if we divide it by sinh squared, we get coth squared phi minus 1 is equal to hyperbolic cosecant squared phi. All right. Now, really, so let me just jump next to the expression that each of these identities is used to, let's say, massage. So we saw this last class. If I have something like a squared, well, let me just write it this way. If x is equal to, let's say, a sine theta, then a squared minus x squared is equal to what? So this identity I really need to look at as 1 minus sine squared theta equals to what? Cosine squared theta, right? So because of this identity, if you multiply that identity by a squared, you get that a squared minus x squared is equal to, in fact, a squared what? Cosine squared theta, right? All right, on the other hand, this identity here, right, if you look at this, we also have what? We've got cos squared phi is equal to what? 1 plus sinh squared phi. See that? So if I have x equals to, if I set x equals to sinh phi, a sinh phi here, then what happens? What simplification does this lead to? You get a squared plus x squared equals to what? Take the green identity and multiply by a squared. Right, a cosh squared. A squared cosh squared, but yeah. And we keep playing this game. Down here, for the tangent one, if I set x equals to a tangent theta, let me use something other than a. Let's say r times tangent theta. Then what? R squared plus x squared is equal to what? R squared secant squared theta. For this one, if I set x equals to r tangent, hyperbolic tangent of phi, then r squared minus x squared is equal to what? R squared hyperbolic secant squared. Let's see here. Down here, if I set x equals to, let's say, r cotangent theta, then x squared plus r squared is equal to r squared cosecant squared theta. Finally, over here, if I set x equals to r coth phi, then x squared minus r squared is equal to r squared hyperbolic cosecant squared phi. All right. So the kind of quadratic expressions we're looking at, they're either of the form, well, I guess there's kind of three things to look at. There's things like a squared minus x squared. There's things like x squared minus a squared. And then there's just sums of squares. These are sort of the three patterns we're dealing with. Right? Either the x squared is subtracted, or the, you see what I'm saying? So if you look at this, there's pairings here. Do you see how they're connected? Which of these is dealing with the same pattern? There's a duality here, right? I can either make a substitution like this, right? What else picks up x squared plus a squared as it reduces this? See this? This also gives you a reduction of something squared plus something squared. So these two substitutions are competing for a certain class of problems as being a viable solution method. What else is in competition? The sine and the tanh substitutions are in competition. See that? This and this. Those both will remove something like a constant squared minus x squared. They'll change it from a difference of squares to just a square, which means we can remove radicals or simplify denominators, as we saw last time. And then, of course, the bottom two also. Oh, what? Oh, man, I probably made a mistake. Hmm. Huh. I thought these came in pairs. How can I get x? Oh. I'm sorry. We actually don't care about cotangent squared. I've looked at this the wrong way. I'm sorry, guys. I'm sorry. You know, it's been 5 years since I've done this. I'm a little rusty. I'm sorry. This is not the way to go. Let me show you why. As an example, suppose I want to do something like integrate one over the square root of x squared minus r squared. So let me show you what we can do. What we can do is we can let x equals to r secant theta. If I do this, I get x squared minus r squared is what? Right? I mean, what I wrote in this bottom segment here, it's not wrong, it's just not something I typically use. What I wanted to say was something like 1 minus, oh man. Sorry, eventually I'll get this. Secant squared theta minus 1, right? Secant squared theta minus 1 is equal to tangent squared theta. That's the identity that I care about. Good grief. Come on, guys. Really? You gonna let me get away with that? You know, I didn't divide by 2 yesterday, and you guys didn't call me out. I didn't divide by 2 the day before that. You guys didn't call me out. You guys got to start, like, you know, following along. Otherwise, there's going to be errors in your notes. It's not good. I mean, if you saw those things and didn't say anything, shame on you. It's here. So there's a place where I solve for 2i and then I divide both sides by 2. I only divided the first term by 2, but I didn't divide the second term by 2 yesterday. And I think it happened the day before that as well. And when I did it in the second section, I made the same mistake, but they called me on it. So I don't know. I guess they're just more confrontational. You guys are just more chill. It's fine. Whatever. Let's see here. Oh, I was going to say x equals 2. Our secant theta is a good match here, because then we have x squared minus r squared is equal to r squared tangent squared theta, which is pretty awesome. Now here, of course, I should have written what? R squared secant squared theta, right? That's x minus r squared, which is r squared times secant squared theta minus 1, which is what? That's r tangent squared theta, right? R squared tangent squared theta. What's dx for this example? Secant tangent, right? In this case, there's an r multiplying it, right? R secant theta, tangent theta. By the way, I'm assuming r is what? A positive constant, right? So dx is r secant tangent d theta. Okay, so there's my trigonometric substitution thought bubble. And let's do it. So what's that give us? The integral of r secant theta, tangent theta d theta, divided by what? Right? And if you'll forgive me, I'm just going to write what? R tangent theta, yeah. Well, this is pretty nice. We're just left with what? The r's cancel. And we're just left with the integral of secant theta d theta. But that we know is a pain to work out. No, it's the natural log of the absolute value of secant theta plus tangent theta plus a constant. Now this problem is very nice in the sense that we can write it in terms of an algebraic expression inside the natural log, right? There's a triangle for this substitution. There's a triangle for half of these substitutions. There's a other thing for the hyperbolic substitutions. All right. Like this one, I guess I should say dx is what? Dx is a cosine theta d theta. For this one, the dx is r secant squared theta d theta, right? For this one, dx is r secant theta tangent theta d theta. For this one, dx is a cosh phi d phi. For this one, dx is equal to, oh man, what did we get for the derivative of hyperbolic tangent? It's still hyperbolic secant squared, right? What about the, about this one? I wonder if I'm making the right comment there, if that was... There are a few other substitutions you could think of, right? Kind of like, I mean, this is a sample 6. I suppose there's a few more you could think of in terms of the one I had written but erased, you know? If you can do these, this should suffice for, like, most problems. Dx is what? Minus r hyperbolic cosecant squared phi d phi. All right, I think. Anyway, all right, so getting back to which problem are we on? This one here, right? We can draw a triangle, right? For the substitution to make the formula nicer at the end. We got a theta. What do we have? We have secant theta is equal to what? It's equal to x over r, right? Which, by the way, should be the hypotenuse divided by the adjacent side, right? For a picture of an acute triangle, because it's 1 over cosine. So where does the x and the r go in my picture? Assuming I'm going to be boring and just use x as the hypotenuse and r as the adjacent side. I mean, of course, there's like an infinite family of similar triangles that you could put different things that would have the same angle. But this one will suffice to capture the relationship between x, r, and the different trigonometric functions. What's the other thing? Remember what I said yesterday? When we do this, the one side of the triangle which isn't immediately given by the substitution will be the thing we're trying to eliminate. See, that happened again. Square root of x squared minus r squared by the Pythagorean theorem, right? So what's secant theta? In view of this triangle, of course secant theta is x over r, right? And what's tangent theta? Right? By the way, did you notice this can be rewritten in a more simple way? I can factor out, right, the 1 over r and what if I have a, this is what? This is natural log of 1 over r, right? Plus the natural log of the absolute value of x plus the square root of x squared minus r squared, plus a constant. And of course, you could just sort of erase this, and just call this c bar or something. I mean, it's just, or you could just call it c. Just lump that into the constant. So the antiderivative that you need here is the natural log of the absolute value of x plus the square root of x squared minus r squared. That's the third kind of trigonometric substitution that I didn't show you yesterday is this one. Yesterday we did an example like this, and we did an example like this. Any questions? Yeah.
Would you prefer we take it all the way down to that bottom step, or are you okay if we stop at the one before?
Well, the bottom step is, I mean, what I'm about to box is the best answer. The answer before is an okay answer, but it's not the best answer. So, let's see here. I mean, I want you to show that you understand the material as deeply as you do, generally speaking. Other questions? There's one. I mean, there's kind of there's a looming large question to ask: why bother with hyperbolic substitutions if the trigonometric substitutions do every pattern that's possible, right? I mean, this, and this. These are the three possible patterns if the quadratic doesn't have a repeated root, right? So why do we need these? Right? Let me show you why. I think it's best for me to show you using the projector a little bit. If nothing else, to draw your attention to the fact that the notes have tons of examples that you should be aware of and should be looking at. I mean, the textbook's good, but on this particular topic, I have taken a fair amount of time to create, I think, decent examples that are helpful. So, all right. So here's an integral. 4x squared plus 9. Well, that's kind of annoying. It doesn't quite fit any of these standard templates, does it? So I have to do something a little bit different. What I want to do basically is make this 4x squared match the 9. So what I do is I let 2x equal 3 tangent theta. See why I do that? If I let 2x, this is on the chapter 9 notes, which are posted on the website, right? This is page 293. Anyway, so I let 2x equal 3 tangent theta. The reason I do that is because then this 4x squared will become a 9 tangent squared theta. And then because tangent squared theta plus 1 is secant squared, I get to collapse this sum into just a single thing, which is what I want. Right? And then 2 dx is 3 secant squared theta d theta. And okay, so then I make the trigonometric substitution. I get this beastly thing. And then, oh no, that's an unhappy place. We went there yesterday, remember it? This you have to do, remember we have to do like a step, we pull out a secant integral, we integrate it, then we do integration by parts, we loop back to minus the integral secant cubed again, and then we solved for this. So this was a non-trivial integral is my point. It's one you don't really want to do if you can get away with it. So trigonometric substitution has led us to an unhappy place here. I mean, we can still do it, right? And you can find an answer, but it's not too happy. And by the way, that's a fairly simple integral, right? Square root of sum of squares is something you'd like to be able to integrate. You can see how that might come up in an application or something. That's not some kind of weird formula. That's a pretty benign looking, not too not too scary looking thing to integrate. Anyway, then we use the triangle idea to simplify this. See, because let me draw the triangle over here. Actually, probably would add something to this example. So my substitution is what? It's 2x. 2x equals to 3 tangent theta, right? So that means tangent theta is what? 2x over 3, right? So I can draw this picture. Theta The opposite side is 2x, the adjacent side is 3. And over here, you've got the square root of 4x squared plus 9. So because of that, you can see then that like the secant theta is what? Secant theta should be hypotenuse over 3. So that's where you get this hypotenuse over 3. And tangent theta is 2x over 3. So you see where those terms are coming from and as you undo the substitution. And likewise over here, it's the product of x over 3, and then that over 3. The 3 times 3 gives you 9. The 9 cancels the 9, which is here, and leaves you with a fourth. Mysterious. Oh, there's a 2 in the tangent, isn't there? Yeah, okay. Do you guys see it? What is the, I mean, is there a particular thing? I mean,
how did you go from the, like, 2x equals, like, from the very start, 2x equals 3 tan theta, and then it becomes 4x squared plus 9 equals 9 tan squared?
so what is, if 2x is equal to 3 tangent theta, then if we square 2x, we get 4x squared, right? But the square of 3 tangent theta is 9 tangent squared theta. So 4x squared is 9 tangent squared theta. If I add 9, I get this, and then, but that's secant squared theta. It's all motivated by all of these substitutions are motivated by these algebraic identifications I wrote over on the sideboard. Those are what are driving my thought process, the knowledge of these trig identities and hyperbolic identities. But, I mean, man, if there was a way to not do that integral of secant cube, this would be better, right? Yep.
How'd you know to add 9 instead of, say, 4? Was it like 3 squared versus 2 squared? Because like the 2x gives you 4x.
Well, I'm trying to reduce 4x squared plus 9, right?
Yeah.
So I know that if I can make this 4x squared term be 9 tangent squared theta, then I know that I'm going to get 9 tangent squared theta plus 9, which will be 9 secant squared theta. So the reason I made 2x equal to 3 tangent theta is because I know that that will make 4x squared equal to 9 tangent squared theta.
By doing that, did you just work it backwards in your head?
Yeah. I have in mind the goal of using these trig identities. 1 minus sine squared is cosine squared. 1 plus tangent squared is secant squared theta. And I know if I multiply these by a number like 9, they're still true. So 9 plus 9 tangent squared theta is 9 secant squared theta. But yes, there is some backwards thinking involved. Absolutely. Now, we'll do some more, don't worry. The other way to do this is with a hyperbolic substitution. So same integral, all right? But this time I have in mind the identity cosh squared is equal to sinh squared plus 1. So basically I want to make, and I multiply this by 9, I get 9 cosh squared is equal to 9 sinh squared plus 9. So I like mix and match. Basically I want to make the 4x squared equal to 9 sinh squared theta. That suggests I make a 2x equals to 3 sinh theta substitution. Because doing this, making 2x equal to 3 sinh theta, will make 4x squared plus 9 just equal to 9 sinh squared plus 9, which is 9 cosh squared. So with that substitution, I make this hyperbolic substitution. I have the square root of 9 cosh squared. The dx is 3 cosh phi d phi over 2, and we're left with 9/2 integral of cosh squared. Well, good news. Integral of cosh squared is an easy integral. That's far less tiresome than the secant cubed, right? In fact, you can just put it back in terms of its definition and work this identity out right quick. Cosh squared of phi is 1/2 cosh 2 phi plus 1/2, right? If you forget this, you could easily derive it, like I did here. And then in view of that, I have this is actually equal to the integral of, 1/2. So the 9/2 becomes 9/4 because of this half. And I have cosh 2 phi plus 1, and I integrate that. And then again, I guess the question is, what's the corresponding triangle for the hyperbolic substitution, right? Let's see here. So what's my... So I'm trying to... Let's see if we can come up with some kind of mnemonic to help us understand how to simplify like this in terms of other things. Oh, goodness gracious. What is sinh of 2 phi? What's the identity for that? I don't know. I don't remember right off the top of my head. What's that? Yeah, I can solve this identity, right? I get 2 cosh squared phi is equal to cosh of 2 phi. There's another. Where should the 1 go? Minus 1. Is this right? I'm trying to solve this identity for cosh 2 phi. Does that make sense? Cosh 2 phi is equal to cosh squared minus a half. Multiply by 2, I get that, right? Did you guys follow me? Since I already have this identity sitting right here, let's just solve for cosh 2 phi. Are you guys with me? Is it plus 1? I moved the half to the other side, though. It doesn't matter. Here, we're going to differentiate this. Because I want to know what sinh 2 phi is. So I get 2 sinh 2 phi, right, is equal to what? 4 cosh phi sinh phi. There's the identity I'm looking for. Sinh of 2 phi is equal to 2 cosh phi sinh phi. So in other words, it's one of these happy places where the hyperbolic and the regular trigonometric functions have the same identity, corresponding identity, right? Okay, so in view of that, I can simplify this here in view of that, right? Now the triangle, that I have in mind is based on the substitution. What's the substitution? What was it? Remind me, guys. 2x equals to what? This time? 3 sinh phi. So a hyperbolic triangle is kind of a funny thing, right? So I don't know. I need some kind of I need some kind of thing to distinguish. I don't know a standard picture for this. So this is just maybe I'll do something like this. It's not a normal triangle. It's kind of like some kind of curved triangle or something. I don't know, however you want to think of it. But if this is phi, if I have A and B here, I know that, well, let me do a more fundamental thing. I've got cosh squared, so suppose I've got cosh phi here, and I got sinh phi here. This is just a picture to organize some identities. Then up here I would have what? I'd have 1, because I have cosh squared minus, but the 1 would be equal to cosh squared minus sinh squared. How to explain this better? I don't know. So if I say this is phi, what's sinh phi equal to? 2x over 3. Man, I don't know. I don't remember how I don't know how. I can't remember how I got from here to here. There must be. I mean, this step to this step makes total sense to me, right? Inverse hyperbolic sine of 2/3 2x over 3. That's just solving the substitution. How do I know that? So what I think I'm claiming here, right, is that cosh is, sinh is 2x over 3. How do I know that cosh is 4x squared? I'm not confident about this red triangle just yet, guys. I'll have to think more about that. I don't want to burden you with something that's not quite right. So I'm going to have to be more algebraic about this. So what we're trying to understand right now is how do you simplify this in terms of an algebraic expression? So sinh phi is easy, right? That's essentially the substitution here, which was what? 2x is equal to 3 sinh phi, right? Is our starting point, right? This is what we know. This is what we said to start with. So we're bound by this and the rules of hyperbolic algebra, hyperbolic functions. So sinh phi is easy. Sinh phi is just 2x over 3. You guys with me on that? That's where this 2x over 3 is coming from. How about the square root of 4x squared plus 9 over 3? How do you see that? Well, I think it comes back to this. Cosh squared phi minus sinh squared phi is equal to 1. So what's that mean? That means that cosh squared phi is what? 1 plus sinh squared phi, but what's that? 1 plus 4x squared over 9. Right? So, cosh phi, being positive, is the square root of 1 plus 4x squared over 9 in this substitution. But you can rewrite this as what? This is the same as the square root of 9 plus 4x squared divided by 3 by algebra. Basically, if I factor a 1/9 out, I have to put a 9 here, and then that comes out to be the third. So I don't know, I would love to tell you I have polished my understanding of the hyperbolic triangle mnemonic. I'm not there yet. Remember, this in some sense is just a mnemonic for remembering how the relations between the tangent and the sine and the cosine work for the trigonometric substitution. I don't know quite how to flesh this out yet for the hyperbolic substitution today. So, yeah.
Well, it looks like it works the same.
Ah. So what triangle would you draw? I'm not disagreeing. I want to follow what you think. So what?
Okay, sinh is 2x over 3, and the opposite would be 2x.
Mm-hmm. So you're saying you're adopting the viewpoint. We can still say something like cosh phi is adjacent over hypotenuse. Sinh phi is opposite over hypotenuse, right? The tangent of phi, I'm guessing, if this and this is the case, it must be the case also that the tangent of phi is opposite over adjacent because tangent is sinh over cosh, right? But what's the rub? What's the one weirdity? The rule between the sides is not governed by the Pythagorean theorem anymore. It's governed by the what? Right. What I'm saying is that if you have if A is equal to cosh phi, right, and B is equal to sinh phi, then this should be 1.
Right, but
And it's also equal to what? It's also equal to A squared minus B squared. That's the... So A squared, what? So how is A related to... Let me just... Sorry. Here's C, here's A, here's B. How are they related?